Welcome, everyone. I am thrilled to have you here. Today, we are exploring a game-changing paradigm in data science using automated machine learning, or AutoML, to orchestrate model training and rapidly discover the optimal models for our business applications. Let's dive in and elevate our MLOps strategy. Let's start with the core concept. What is automated machine learning? In Azure Machine Learning, AutoML is an orchestration engine that automatically searches through a vast library of algorithms and pre-processing configurations. The basics are simple. Instead of training one model at a time, AutoML runs multiple training jobs in parallel. Why is this revolutionary? Because when you are asked to build a model, you rarely know upfront which specific algorithm will give you the best results. Finding that right combination traditionally requires endless guesswork and manual experimentation. How do we fix this? By letting the cloud do the heavy lifting. You provide the data and the task, and AutoML explores the model space for you. For a deep dive, understand that AutoML is intelligent. It uses meta-learning to look at your data's shape and distribution, instantly narrowing down thousands of possibilities to the few pipelines most likely to succeed. This eliminates the manual bottleneck and accelerates your time to value. Take a look at this flowchart, which maps out the AutoML orchestration process. On the left, we start with our input dataset. This data flows directly into the AutoML orchestrator in the center. Notice how the orchestrator fans out into multiple parallel branches. Instead of a linear, sequential process, Azure is simultaneously spinning up compute nodes to test algorithm A with configuration X, algorithm B with configuration Y, and so on. These parallel runs generate trained models, which all flow into the compare and rank node. Here, the system evaluates their performance against your chosen metric. Finally, it outputs the absolute best performing model on the right. This visual perfectly captures how automation replaces manual trial and error with massive, parallelized cloud computing. To truly appreciate AutoML, we must understand the problem it solves. What does traditional model training look like? It is highly manual. The basics involve a data scientist manually selecting a single algorithm, writing the training script, executing it, waiting for the results, and then starting the entire process over again. Why is this a problem for modern enterprises? Because this sequential approach is incredibly inefficient. It wastes expensive data science talent on repetitive tasks rather than solving complex business logic. How does AutoML change this? It completely replaces the manual loop by automating the execution of dozens of models simultaneously. Let's take a deep dive into human behavior here. When engineers test manually, they often suffer from cognitive bias. They tend to stick to the algorithms they know best, like random forests or logistic regression, potentially missing a lesser-known but highly effective algorithm that would perform much better on this specific dataset. AutoML removes human bias entirely, exploring the search space objectively and comprehensively. This diagram clearly contrasts the two paradigms of model training. In the top block, we see the manual ML workflow. It is a closed, slow loop, write code, train a single model, evaluate, and iterate back to the start. It is heavily reliant on human speed, which leads to the delayed deployment bottleneck below. Now look at the bottom block, the AutoML workflow. It is streamlined and scalable. We simply define our constraints, and the system immediately transitions into parallel cloud execution, followed by automated ranking. There are no slow iteration loops here. This modern architecture points directly to rapid production, demonstrating exactly why orchestrating training with AutoML is a fundamental requirement for scaling AI operations in an enterprise. A model is only as good as the data fed into it. This brings us to data pre-processing and featurization. What is featurization? It is the vital step of transforming raw, messy business data into clean, mathematical vectors that algorithms can process. The basics include imputing missing values, scaling numbers, and encoding text categories into numerics. Why is this critical? Because if you feed unnormalized data into a model, large-scale numbers will completely drown out the predictive power of smaller-scale numbers. How do we handle this in AutoML? You can set the featurization mode. If you have already perfectly cleaned your data, you can set it to off. If you want to force specific rules, use custom. But the deep dive here is the auto setting. When set to auto, Azure Machine Learning acts as an intelligent data engineer. It applies built-in data guardrails, automatically testing various imputation strategies and scalars in tandem with the algorithms to find the perfect mathematical representation of your dataset. Let's trace the data preparation journey in this flowchart. On the left, we begin with raw tabular data. This data enters the featurization mode decision node. If a data scientist selects off, the data bypasses pre-processing and goes directly to training, assuming it is already perfectly clean. If they select custom, it follows the path to user-defined steps. But the magic happens on the auto path. The data routes through Azure Data Guardrails, which automatically perform scaling, missing value imputation, and categorical encoding. Both the auto and custom paths ultimately converge into the optimized feature set node on the right, ensuring the downstream algorithms receive highly structured, mathematically sound data. When AutoML tests 50 different models, how does it know which one is the best? It requires a target. What we are defining here is the optimization metric. The primary metric is the exact mathematical criteria the engine uses to rank success. The basics include familiar terms, accuracy, precision, recall, and AUC. Why do we need to be careful here? Because if you give the engine the wrong target, it will successfully optimize for the wrong business outcome. How do we set this? When writing the code to submit our job, we explicitly set the primary metric parameter, for example, setting primary metric equals AUC weighted. Let's deep dive into why that specific metric matters. In many business datasets, classes are imbalanced. For instance, 90% of transactions are normal and 10% are fraudulent. If you optimize for accuracy, a model that simply guesses normal every time will be 90% accurate but entirely useless. By optimizing for AUC weighted, the engine is forced to evaluate how well the model distinguishes between both classes, yielding a truly performant model. This diagram illustrates the metric selection process. It starts at the AutoML configuration node, leading directly into the crucial decision: select primary metric. We highlight two paths based on your dataset. If your data is highly imbalanced, you take the left path and configure AUC weighted. If it is perfectly balanced, you might select accuracy. Both metrics feed directly into the model evaluation engine. As parallel models finish training, this engine uses your chosen metric to instantly rank the models from highest to lowest score, culminating in the automatic selection of the absolute best model. It is a completely objective, data-driven tournament. Finding the right algorithm is only half the battle. The other half is configuring it correctly. What is this called? Hyperparameter tuning. The basics of tuning involve adjusting settings like the learning rate of a neural network or the maximum depth of a decision tree. Why is this necessary? Because algorithms are not one-size-fits-all. Even the most powerful algorithm will underperform if its settings are left at their default values. How does AutoML handle this? It orchestrates a sweep job behind the scenes. It defines a search space and samples different combinations automatically. For our deep dive, let's look at cost optimization. Testing every combination is impossibly expensive. Therefore, Azure utilizes early termination policies. As the models train, the orchestrator monitors their real-time performance. If a specific hyperparameter combination is clearly failing early in the training process, the system automatically terminates that specific run. This ensures your compute budget is strictly spent on the most promising models. Let's follow the hyperparameter sweep logic in this flowchart. After an algorithm is selected on the left, it enters the hyperparameter search space. The system spins up multiple trials, shown as combination 1, 2, and n. Each of these runs hits the diamond-shaped node, the early termination check. This is your cost-saving gatekeeper. If a run shows poor performance early on, the path points straight to kill run and save cost, immediately shutting down that compute node. If it shows good performance, it is allowed to complete training and log its final metric. This intelligent routing ensures high efficiency during massive-scale experimentation. With all this automated activity happening, how do we keep track of it all? This is where MLflow comes in. What is MLflow? It is an open-source platform designed to manage the machine learning lifecycle, and it is natively integrated into Azure Machine Learning. The basics are straightforward. MLflow tracks the parameters, metrics, and artifacts for every single run generated by your AutoML experiment. Why do you absolutely need this? Because when AutoML spins up 50 parallel training jobs, you cannot rely on manual notes. You need a searchable, immutable ledger to compare results and guarantee reproducibility. How does it work? It happens automatically in AutoML, but you can also configure MLflow for custom tracking inside your Jupyter notebooks. Deep diving into deployment, MLflow does something brilliant. It logs the exact Python environment dependencies alongside the model weights. When you are ready to deploy the winning model, MLflow packages it perfectly, ensuring there are no missing libraries in production. Look at the MFlow architecture on your screen. The AutoML parallel runs at the top are actively streaming telemetry down into the central MFlow tracking server. This server acts as the master database, splitting the incoming data into three crucial components: the metrics dashboard for your scores, the artifact store for your model files, and the environment dependencies mapping the required software packages. These components all feed into the compare runs node. Once you visually review the data and identify the champion, you move to the final step, registering the winning model. MFlow ensures that nothing is lost in translation between the training compute and the final registry. We have found the model with the highest metric, but is it safe to deploy? We must evaluate it using the Responsible AI dashboard. What is this? It is a suite of diagnostic tools within Azure Machine Learning that assesses fairness, explainability, and error distribution. The basics dictate that before any winning model touches production, it must be audited for bias. Why is this a mandatory step? Because a model might achieve a fantastic overall score, but still fail catastrophically for a specific demographic like age or gender. Deploying a biased model poses severe reputational and legal risks to your business. How do you prevent this? You generate a responsible AI dashboard against your newly trained model. Taking a deep dive into the dashboard, you will find error analysis. This feature uses a decision tree to visually isolate and highlight the specific data cohorts where your model is making the most mistakes, giving you the transparency required to make an ethical deployment decision. This flowchart maps the critical responsible AI validation gate. The winning AutoML model flows into the responsible AI dashboard, triggering three distinct analytical views. Feature importance tells you which data points drove the predictions. The fairness assessment checks for demographic bias. Error analysis highlights hidden failure pockets. These insights converge at the decision gate, passes business and ethical rules. If the model shows bias, it follows the no path and is rejected back for retraining. If it passes, it moves forward to approved for deployment. This visual underscores that high accuracy alone is never enough. Models must be transparent and fair. To bring this all together, let's examine a critical real-world use case. Meet Prosware, an innovative healthcare startup. They are building a web application to help practitioners diagnose diabetes in patients. The basics: their data science team has excellent historical patient data, but they simply do not have the time to manually test dozens of different classification algorithms. Why turn to automation? Because in healthcare, accuracy and time to market are critical. Manual experimentation would delay their launch by weeks. How do they solve this? By orchestrating an AutoML experiment. They feed the patient data into Azure Machine Learning and set the primary metric to AUC weighted to handle class imbalances perfectly. The deep dive realization is the end-to-end synergy. AutoML tests the models in parallel, MFlow seamlessly tracks every metric and dependency. And the responsible AI dashboard proves the winning algorithm is fair across all patient demographics. Once validated, Prosware securely deploys the model to an online endpoint, delivering life-saving insights to practitioners instantly. That is the true power of automated machine learning. Let's review the end-to-end Prosware architecture. Starting at the top left, patient medical data flows into the AutoML orchestrator. The orchestrator triggers parallel model training, actively optimizing for the AUC-weighted metric. This highly efficient loop is continuously tracked via MFlow, resulting in the selection of the winning diabetes model. Before touching the real world, the model passes through the responsible AI fairness check. Upon approval, it is pushed to an online endpoint. Notice the two-way communication at the bottom. The practitioner web app securely calls this endpoint in real time, providing immediate diagnostic insights to the doctors. This illustrates a complete, automated, and responsible AI pipeline.